All right, so in this video, we're going to take a look at just a couple of different curves that we use parametric equations for, or at least easily, right? We can see the advantages of using a parametric equations to draw curves that can be really complex, but the equations themselves are pretty straightforward, right? Now, the first one is what's called a cycloid, right? So if we imagine that there is just kind of a wheel and there's like a point on the wheel and you just want to trace the path that it takes, right? That can easily be done with parametric equations, right? If you look here, right, these are the parametric equations, right? They're pretty basic and they can allow us to do something like trace the path of a curve, right? Here, if we just let it play out, think of that circle as the wheel, and then you can see the path that it traces out of a point on the wheel, or you can think of maybe there's some kind of bug at the end of that wheel there and it's stationary, and we just kind of trace the path that it takes as the wheel kind of progresses there. All right. Okay. So that's what we call just a cycloid, right? Pretty straightforward, right? Simple path, right? Just a wheel on the ground traveling and then the path of a particular point here. Now, a more interesting type of curve, it's what's called a hypocycloid. Right now here, the equations themselves, they are a bit more involved than the cycloid, but still, compared to what we can draw, they're not overly complicated. Right? Like if you remember the variables t, a and b are constants that, well, let me just show you here. So here, instead of the wheel here, if we think of the smaller circle of a wheel traveling on the ground, think of it traveling inside a circle here. All right, and if we trace out the path that it takes, right here, let me slow it down here. Okay, so we could see here. All right. We could see here as it kind of flows here. All right, it goes something like that. Right now, we can vary the radius of the outer circle, right, and the inner circle. All right, and you can see that has an effect on what the path looks like. All right, so as it turns out, these two constants, these a minus a over b, or a and b, if you take the ratio of these, a over b, this gives me the number of cusps. Right, so when we have something that, let's see here, 6 over 2, all right, that is 3, so we have 3 cusps, right? No matter how many rotations I get, right? I can keep going and going, but it just goes those 3, right? And we can kind of vary this here. So let's go all the way to 10. Let's zoom out here. And just starting from the beginning, right? And 10 over 2. You can see here 5, right? Once those initial 5 get drawn out, right, then that rotation just keeps going and going over those same cusps. Right. All right. Now so here, let's kind of get this here. All right, let's say 2 is like some kind of decimal here, and we could see how that affects the number of cusps, right, when we do that division here. Right, so you can see we could get some interesting curves here, right, but just varying the values of a and b, even though the basic equations themselves, they're pretty straightforward, right? Remember the variables t, right? So it's just a sum and difference of sine and cosine. Now, one thing that is interesting about these is when you, so here, when you have the A over B, the ratio be an irrational number, right? So the previous graph just had us looking at rational numbers, but let's say that it was an irrational number. Let's say pi. Right. Let's kind of zoom in here, get a better view here. Right. And here's set at 1,000 rotations, and we could see here, right, when we have an irrational number, right, when A over B here essentially is just pi, well, what happens is we have infinite number of cusps, right? So those rotations, each rotation that's taken is a new path, right? So essentially, if we just keep going and going and going and going, right, then it's just space filling, right? It's filling up all that space, right? So this kind of is capped at 1,000, right? So really just capped at just kind of the pixels of the graph itself, but right, all of the inner and the between the larger radius and the inner radius, it'll just be filled, right? If we just trace the path, it'll fill it completely, right? As the path keep going and going. So that's an interesting thing that happens when the ratio happens to be an irrational number. All right, so here we see an example of just some parametric curves that lead us to have just some interesting shapes, right?